Good afternoon. Today we will talk about NMR spectroscopy. NMR stands for nuclear magnetic resonance. And nuclear magnetic resonance is the most powerful techniques for identification of organic compounds. We've seen already that we can use mass spectrometry to establish the mass of organic compound as well as to identify the presence of bromines, chlorines, and nitrogens. Also, we've seen how we can use IR spectroscopy to identify functional. However, neither of these two techniques comes even close in generality to nuclear magnetic resonance. And nuclear magnetic resonance is able to be such a general overwhelming technique because it is able to identify virtually any molecule which has either protons or carbon-13, which is the majority of organic molecules, in addition to some other nuclei such as fluorine, phosphorus, nitrogen, etc. Since pretty much any organic molecule will have either protons or hydrogens, the nuclear magnetic resonance can be used in a very general context, and oftentimes the structure of an organic compound can be elucidated solely by using NMR. Okay? We will not go into the details of how NMR actually works. We will focus mostly on its applications and the interpretation of NMR spectra. But not all nuclei are NMR active. NMR stands for nuclear magnetic resonance, and nuclear comes from the fact that nuclear magnetic resonance follows the changes in the nuclear magnetic spin in nuclei of a certain compound. And not all nuclei are NMR active. In order for a nucleus to be an NMR active nucleus, it needs to have an odd atomic number or an odd mass number. In other words, it needs to have either an odd number of protons or an odd sum of the number of protons and neutrons. Okay? If the nucleus satisfies either one of these two conditions, then it will behave like a little magnet. It will have this magnetic momentum, which will be non-zero, and that magnetic momentum will dictate that the nucleus orients itself in the presence of external magnetic field, B0, in a certain fashion. If the nucleus orients itself, aligns itself with a field, then we will call this state an alpha state, and this will be a lower energy. If the nucleus aligns itself in the direction against the field, and this will be called the beta state, which will have higher energy than the alpha. Okay? Now, this difference in energy between the alpha and the beta state is the delta E, and this difference corresponds to a quantum of electromagnetic light, h nu. In this case, this h nu is in the radio wave reach. However, this frequency or this energy also correlates with the strength of the magnetic field through this equation, where B is magnetic field that the nucleus is exposed to. Gamma stands for gyromagnetic ratio, which is a constant, but it varies with the nucleus. So it's a certain value for every given nucleus. And age is Planck's constant, and 2 pi is just a number. And if you look at this equation, then this all looks very nice, but it would imply that all nuclei have a certain set frequency, which is determined solely by the gyromagnetic ratio and magnetic field. And that would be fine, except it would not allow us to distinguish between different types of nuclei of the same kind. Fortunately, this magnetic field is not equal only to the external magnetic field, but is influenced by the electronic surroundings of a nucleus. So in other words, this effective magnetic field B equals B0 minus B shielding. And this B shielding is a small magnetic field caused by the electrons that surround a given nucleus. B shielding is really orders of magnitude smaller than B0. And so we're measuring very small differences in the NMR, which is a bit of a problem, but it's a problem that can be overcome. And this shielding now allows us to distinguish between different types of nuclei, because in an organic molecule they have different surroundings, which will then allow us to look at things and see different shielding values, thus identifying different protons. To illustrate this in an example, if we look at the simple molecule of methanol, this methanol will have protons which are closer to the carbon, and since carbon is not very electronegative, these will have a lot of electrons around them, and it will be what is known as shielding. On the other hand, we will have these oxygens which are next to the hydrogen. We have these hydrogens which are next to oxygen, and these will be de-shielded because oxygen will pull most of its electron density towards itself, thus relieving protons of it. And in other words, we will be able to see two peaks in the NMR spectrum, one coming from the methyl group, one coming from the OH group, which would indicate their inequivalence. Okay? So let's look now at what pieces of information we should be looking for in an NMR spectrum in order to get the most out of it. We basically are going to need 4 pieces of information. First one will be the number of peaks. In the given molecule of methanol, CH3OH, we will have 2 peaks because we will have CH3 protons, all of which are equivalent with each other, and the OH proton, which will be the other kind of a proton present in this molecule. Another piece of to give you some more examples of this analysis, in methane we will have only one type of protons because they're all the same. In ethane, again, we will have only one type of protons because there's a plane of symmetry which relates these two methyl groups. And these protons, just like in the others, are called chemically equivalent. If we move to a molecule of propane, propane will now have 2 different types of protons, the central ones and the terminal ones, so this will give us the rise to 2 peaks. If we go to ethene, all 4 peaks again are related by symmetry, so this is just 1 peak. But if we replace one of the hydrogens with, say, fluorine, then we desymmetrize the system completely and we get 3 peaks because these two are not interchangeable. One will always be cis to fluorine, one will always be trans, which means that the chemical environments are different and things have changed there. If you look at the molecule of dimethylbenzene, this will have two different kinds of peaks, one associated with methyl group and this one. All 4 of these will be the same, and so on. Okay. So the number of peaks is the first piece of information which tells us a lot about the symmetry of the molecule and the number of different proton groups that we have on it. The second piece of information is the positions of peaks. The positions are directly related to the amount of shielding or de-shielding that a certain peak experiences, and thus allows us to tell something about the chemical environment of the peak, whether it's shielding or de-shielding, whether we have electronegative elements or not. Third piece of information is the intensities of peaks. Intensity of peaks, as we'll see later, is related to the number of protons that correspond to that. So, for example, in a molecule of methanol, we have 3 equivalent protons on the methyl group and 1 equivalent proton on the OH group. So we would expect the peak for the methyl group to be larger, and indeed it is. And we can figure out the number of protons taking backwards from the ratio of these peaks. And finally, the most complex, but also the most useful piece of information is the shape of peaks, or peak shape, also commonly referred to as peak splitting. This slightly intricate phenomenon allows us to establish the immediate neighborhood of our protons. And this turns out to be extremely powerful because you can very quickly make connections between the certain fragment of a molecule and its immediate neighbors, which allow us to very quickly get to the structure of a molecule as a whole. We will now go into details. We sort of analyzed the first type already, but now we will go into details of analysis of the points B, C, and D, and we'll see some actual NMR spectra.